connected to the engines. A new nose section housed a 12-ton lead and rubber shielded compartment for the crew of 5: pilot, co-pilot, flight engineer, and 2 nuclear engineers. There were also water jackets in the fuselage and behind the crew compartment to absorb radiation from the reactor.
After conversion, the aircraft was redesignated the NB-36, the N standing for nuclear. What they did was they took an actual working nuclear reactor and they put it in the aft bomb bay and they flew with it. And the point being, could you protect the crew from the radiation from a working reactor?
The whole essence of this experiment was simply to test whether you could fly a nuclear reactor in an aircraft and not kill the crew through radiation while doing it.
If you couldn't solve that problem, then it didn't matter whether you could make the engines work. No one would fly it.
The first flight of the NB-36 with its atomic reactor was on September the 17th, 1955. The pilots christened their aircraft the Crusader. The tests proved that the radiation could be contained, provided there was heavy shielding. Atomic-powered flight was a step closer. But now, another problem had to be resolved. It was all very well flying with a reactor, but what happened if you crashed? Because of this danger, the Air Force took very special precautions. Flying beside the NB-36 on every mission was an Air Force transport plane carrying a platoon of Marines.
The plan was that if ever the NB-36 crashed, the Marines in the accompanying aircraft would instantly parachute out, seal off the crash site from prying eyes, and obviously to protect any nosy civilians. That could have been quite dangerous, and the Marines being the Marines, they nicknamed this unit the Glow-in-the-Dark Brigade.
Between 1955 and 1957, the NB-36 made 47 successful flights.
The problem now was to get an actual working aircraft into the air. And the division of labor was that the Air Force would provide the airframe and the Atomic Energy Commission would provide the working engine.
The planned propulsion system would weigh 80 tons. The whole nuclear engine unit, including the reactor, was to be built as a single module and removable for refueling and repair. The challenge now was to get an atom-powered engine to work in flight. An ordinary jet engine works by sucking in air through an intake and compressing it. This means that more of the oxygen required to burn the fuel is squeezed into the combustion chamber. The aviation fuel then burns with the oxygen, causing continuous rapid heating of the air. This heated air expands rapidly, creating thrust to propel the aircraft forward. A jet engine can attain great speed. However, there is a drawback. A fast jet engine is fuel hungry, yet the aircraft can carry only so much aviation fuel. That is why modern military jets are so dependent on in-flight refueling. But an atomic motor would solve this problem. The fuel-oxygen combustion process is replaced with the heat from the reactor, which lasts for months or years at a time.
The theory of an atomic engine is very simple. In fact, it's simpler than a jet engine. You simply take the air and you put it into the reactor, which suddenly heats it up. It's not even a chemical reaction. The air just expands, pops out the other end, and pushes the plane forward.
The theory was simple, but the engineering was not. The scientists of the Atomic Energy Commission came up with two competing ways to build an atomic jet engine.
There were two main approaches to nuclear aircraft propulsion. One of them involved reactors that simply had longitudinal holes, and the air came in one end cold, passed through fine holes inside the reactor, became very strongly heated, and produced thrust coming out the other end. Well, the advantage of direct power is that it's simpler. there are almost no moving parts. The air goes into the reactor, passes through a lot of little holes through the reactor, comes out hot. So in principle, it's simpler.
But this so-called direct cycle engine proved to have a major drawback.
The downside to the direct cycle method is that it's very easy for the air passing through the reactor core to become irradiated, either directly if the shielding is weak, or if in the course of time with the heat and dynamic pressures the shielding begins to break down and the irradiated materials begin to flow out of the reactor core, in which case you are spewing dirty material at the back of the aircraft.
That led the Atomic Energy Commission scientists to propose a second kind of atomic motor called the indirect cycle.
The other approach was to have a reactor separate from the propulsion system, but on the airplane, of course, which would produce lots of energy, heat. Then that energy would be transferred from the reactor to a propulsion unit, a jet-like propulsion unit, through the use of hot liquid metals.
The indirect cycle has the advantage that you avoid passing the air through the reactor. Therefore, you're going to avoid the problem of any irradiated materials exiting the plane. So what you have to do is to have some medium between the air and the hot reactor, some other substance that will pass from the hot reactor, taking heat, and transfer it to the air. But that means a lot of plumbing, and it's very heavy, and it's difficult for an aircraft.
There were now two competing atomic motors, the simple but more dangerous direct system, and the safer but complex and heavier indirect system.
In the race to build the first atomic engine, the General Electric company opted for the direct cycle, the simpler, though potentially dirty system. The Pratt & Whitney company opted for the indirect cycle, safer but more complex to engineer.
While testing of the NB-36 continued and work on the nuclear engines got underway, General LeMay and the Air Force drew up plans for a real atomic bomber.